Okay, good morning. So we continue the next part of the lesson. That's also a very big part of this chapter, trigonometric identities. But of course, you have to be good in algebra if you want to solve a little bit harder problems in this area. And the questions are the book are considerably in a good level, I think. So what do we mean by identities? Let me just briefly remind you what do I mean by an identity. For example, when we say algebraic identity, so this is one of the famous algebraic identities, yes? So you can say that x plus 1 to the power of 2. So let me write x plus y to the power of 2 is x squared plus 2x squared, 2xy plus y squared. That is called an algebraic identity. So what does it mean? It means that you expect to have equality sign, and then when you say it is identity rather than being an equation, it means that it is true for all possible choices of x and y. So it means that it doesn't matter what values you choose for x and y, the left-hand side becomes equal to the right-hand side regardless of the values you choose, yes? This is algebraic identity. The notion of identity is the same in this lesson, but trigonometric identity is clear. It is true equalities involving trigonometry. So that's a trigonometric identity. The most famous trigonometric identity ever is which one? The most famous one is you have sine of an angle squared plus cosine of the same angle squared is always regardless of the value of theta is equal to 1. So that's the most famous trigonometric identity. So this is in the formula sheet, but I really want you to memorize that. It is not something hard. And let me just emphasize that I have seen some students, for some reason, they take a square root from this. And of course, this part is completely correct. So far, so good. And the square root of 1 is 1. But be careful, so I have seen students sometimes write this, which is not correct. The reason is that square root of a squared plus b squared is not equal to the first one squared plus the second one. This is not correct. So you cannot get rid of the powers of 2 by no means, yes? So you have to live it. And of course, this is also good to know it in two different ways. So sine squared theta from this equation, you can move this to the other side. This is also good sometimes to know. So in some problems, you need to get rid of sine in favor of cosine. Let us say sine squared in favor of cosine squared. Then you can use this. Or, of course, the other version of this, yes? So these are not new formulas. So I have written it in three different ways, but they are actually one identity, and that's the line. Before continuing to the main topic of today's lesson, I want to start with two examples. These two examples are actually important to remember the method for solving them. Okay, so this is one of the exercises. Example. And I put a star on it because I want you to, not because this is hard, this is actually extremely simple, but this is one of those prototype examples that you need to have in mind. So, I would say let sine theta be equal to, say, for example, minus 1 over 3, and let theta be in the first quadrant. Sorry. In the first quadrant is contradiction, yes? Because in the first quadrant, sign cannot be negative. So let us make it in the third quadrant. Yes? Determine the exact value of sine and cosine and tangent. Sorry, red values off, yes. Okay. So first of all, let me just give you a little bit of warning. So I have seen students start solving this. If this is in my exam, so usually in my exam calculator is allowed. Okay, so in principle, the solution that they present is not completely wrong. Actually, it is good. So what they do, they just take the calculator and say that theta is sine inverse of minus a third. Of course, it is clear that they get a number, and then they calculate when they have the theta, they use the calculator again to calculate cosine of that angle and calculate the tangent of an angle. Okay. The first thing is that in this solution, of course, the calculator is allowed. The second thing is that even if the calculator is allowed, you are not able to get the exact values. Because I have intentionally chosen the numbers so they are not famous. So the calculator will provide you with decimal numbers which are not the exact values. So this is important. When I say exact value, even though technically this method is right, nothing wrong with it. Yes, but this is not what I mean in this problem. I really mean exact values. Yes?
If you want to type exact values, couldn't you just write cosine of sine inverse of a minus 1/3?
Yes, that is a little bit, I would call that this is state cheating.
What?
Yes. So, but determine the exact values. The values are actually, you are right. In principle, you can write this. You can write cosine of sine inverse, but this is a little bit symbolic. Yes. The reason I don't agree with that, because if you can provide a simple answer, this is not wrong, this is right, this is the exact value of what I mean. But if the exact value is supposed to be 5/10 or something, if you provide this, it's not acceptable, not because this is not exact value, because it is not a simplified version. Okay, so it's always in mathematics, whenever you can provide a simple answer, you have to provide the simplest possible one. So I will never ever mention that simplify the answer. Okay. So in that perspective, yes, this is the exact value. This is not value, by the way. This is the symbol for the exact value. Yes. But here we can calculate the exact value. So the star for it tells you that this is an important problem, not because this is hard, because it happens a lot of places in trigonometry. And this idea is to use this identity. So I give you sine. You have this identity in mind or in the formula sheet, so you use it in a proper way. What do I mean? So you have sine. So let me write the identity here. Yes. Instead of sine, you put minus a third, which is given to you in the problem. Cosine is missing. That's good, because I want to find it, what is demanded in the problem, yes? This 1 to power 2 is 1/9. I move it to the other side, it becomes 1 minus 1/9 is equal to cosine to the power of 2 theta. And if 1 minus 1/9 is 8/9. But this is cosine squared. I am looking for cosine. So cosine is plus or minus the square root of 8/9. Let us simplify this a little bit, because I want to have exact values. So square root of 9 is exactly 3. Square root of 8 is not a complete square, so I have to keep it like that. But 8 itself is 2 times 4, so I can write it as 2 square root of 2. It is not mandatory. If you just write the square root of 8, that's also acceptable. Yes?
Shouldn't the negative symbol be in parentheses, because it's on a trigonometric identities, and they are for the most part positive?
No, there is not in most part. So you see this is trigonometry, but this is negative.
But I mean like plus minus.
No, You have to be patient,
Yeah,
yes?
I can understand. All right.
But then you have to use this part. Yes? So it is mentioned that a theta is in the third quadrant. And in the third quadrant, you know that x coordinate is negative. And so it means cosine cannot be the positive number. So you have to choose the negative. So you would write that since theta is in the third quadrant, cosine theta is negative. Okay? So this means that the positive one is not acceptable for this kind of situation. Yes? Yes? So for example, if it were in the fourth quadrant, then I have to choose the positive one. Yes?
Yeah, that's what I meant. I meant like you put it in parentheses, the negative or the plus symbol.
No, I don't understand. Do you mean this?
Yeah, the plus symbol. No, the plus. Yeah, the plus symbol. You put it in parentheses because it's not in use. Don't you do that?
No, I don't do that. I do this. Yes? Why should I put it in parentheses? I don't understand. Because there are two solutions for this. You should have a reason to throw one of them away. So first you calculate both of them, and you need to have a line of reasoning why you want to throw the other one away. So anyway, cosine theta becomes 2 square root of 2 over 3 with the negative sign. And this is the exact value. Of course, you might say that, okay, this is also a little bit cheating. What is this exact value? I hope that you agree with me. That number is much better than this simple. Even though that number is also a little bit square root of 2, what the square root of 2 is. Yes, but we know square root of 2 better than that simple. Yes? Anyway, so that is the exact value for cosine. Then hopefully everyone can tell me what is tangent, because tangent is sine over cosine. Yes, so tangent of theta is sine over cosine. Sine was given to me from the beginning. It's minus a third. And then cosine, I just calculated it. And then what happens? So this 3 and that 3 are cancelled. So it becomes 1 over 2 square root of 2. So this is also the exact value for tangent, and this problem is solved. In principle, I can give you cosine and ask you for sine and tangent, but I hope that you see that this problem is very similar. Yes, I use this identity again, but this time instead of cosine, I put the number given into me, to me, and then I find sine, and after that, again, I can find tangent. So this is why I don't want to give you another example by changing the question from having sine to having cosine. That's completely simple. But I will also change the problem if I give you tangent and I ask you for sine and cosine. That is also the second important example. Again, simple, but I want you to know about it. Okay, so this time I give you tangent and I ask you for the other values. So I would say that let tangent theta be equal to, say, for example, minus 3, and let theta be in the second quadrant. Determine the exact values of sine theta and cosine theta. Okay, so these two problems I really want you to understand, not because they are hard, because it is necessary, especially when we continue in our lesson. Yes? Okay, what do you think I should do this time? Because in the previous case, I started from my identity. Because one of them was given, one of them was unknown. For this problem, if I start with this identity straight away, then I have two unknowns because neither sine is given nor cosine. So what do you think I should do? Yes?
You write like sine over cosine is equal to minus.
This is actually the first starting point. It's natural because the only piece of information that I got from the problem is this one. Yes? So let us just work a little bit with it. And of course, my question mark is on sine and cosine. So it would be a good idea to rewrite tangent in terms of sine and cosine because I need them. Yes? That's a good point. But still, it's not enough because, so I would say tangent of theta is given to me to be minus 3. And then instead of this, you told me I write it sine theta over cosine theta. Everything is so far so good. Then what? Still, I cannot find sine, I cannot find cosine because there are two unknowns involved and I have one piece of information. But another, yes?
You could just like multiply one of them.
Okay, so let us just do that one. So I multiply everything by cosine, sorry. This becomes minus 3 cosine theta. Okay, so that's it. But still, there are two unknowns. Yes?
Can you put this in the original formula?
Yeah, we can just use another piece of information that we always have. They don't mention it, but you need to remember it, okay? So we have this formula as well, but instead of sine, I can substitute minus 3 cosine theta. So I put it here, so this becomes minus 3 cosine theta, totally squared, and then I have plus cosine squared theta is equal to 1. And then I raise it to power 2, it becomes what? It becomes 9 cosine squared theta, and then plus cosine squared theta is equal to 1. 9, 1 more, I have 10. This becomes 10 cosine squared theta is equal to 1. This means that cosine squared theta is 1 over 10. I am looking for cosine, so I take the square root, but I don't forget to write plus or minus, and I have to keep exact values. So don't put this number in your calculator. Just keep it like that. But then, of course, both of them might happen, but not under these conditions, because it is mentioned that theta is in the second quadrant. So in the second quadrant, cosine is negative. So I would say, yeah, just write something to show that you know about this. Since theta is in the second quadrant, yes, cosine theta should be negative. So therefore, the answer that you have to provide for cosine is negative 1 over square root of 10. So the first one is answered. Now you want to find sine theta. So what is your suggestion to do that? Yes?
We put that back in the sine formula.
Which one?
And
Here.
minus 3
Yeah, this is
cosine.
better.
Yeah.
You can put it back here as well, but the calculation, the final answer will be the same. But definitely this one is superior to that, yes? So what you need to do, whatever you got for cosine, you multiply it by minus 3, and this is your sine. I just talked about this orally, but sine theta, multiply this by minus 3, it becomes positive. Is it consistent with your intuition? Did you expect sine theta turns out to be positive? Yes, because it is in the second quadrant. In the second quadrant, y coordinate is still positive. This is completely correct. So this example, I really want you to have these two examples. So remember that if one of these values are given, you should be able to find the other two. Okay? So now we go to the important part of today's lesson. So, and then there is nothing that I teach you. So what you need to learn, you need to remember whatever we learned about algebraic identities. You need to learn whatever we learned about factorization in Math 3C, or rational expressions if you want to go harder problems. And of course, you have some you should have some experience here to solve the problems. Okay, let me start with one example. Okay, so the only thing that I can do for you is to solve a diversity of problems and examples so that you can get familiar with the tricks and techniques that you need to use here. There is nothing new, there is no new lesson, neither in algebra nor in trigonometry, yes? Okay, so I would say that show, so I can say that show or prove. So let me use the word, mathematical word, prove the following identities. By the way, let me emphasize again, when I say prove or show, but for an equation I ask to solve, okay? So number one, by the way, this one that I write here, we will need it in derivative chapter. So I also recommend you to have it in your memory. And in the university, sooner or later, you have to memorize it. Prove the following identities. This is number one. I want to show that 1 plus tangent of an angle squared is equal to 1 over cosine of that angle squared. And by the way, let me mention one thing in passing, that whenever I ask you prove the following identities, it means that whenever they are meaningful, they are correct. For example, this identity is not valid if x is 90 degrees. Because if x is 90 degrees, cosine of 90 degrees is 0, and then 1 over 0 is meaningless. So whenever I ask you to prove, to be honest, if I want to mention it in a very rigorous way, I have to ask you, prove the following identity whenever cosine x is not 0. But this part is implicitly in the problem itself, so I will never ever mention it. When I ask you to prove the following identity, I mean prove the identity in the domain of the validity of that identity. Yes? That is one thing that I want you to remember. So the second thing is how we should do in this one. So there is no particular way that I can teach you unless I can draw your attention to some points. Yes? So for example, if you want to prove an identity, you have to be a little bit organized. You will start from one side and try to do some algebra and then reach to the other side. Which side you choose to start with, I would recommend to start with the complicated one. Yes? Because our brain has evolved to make things simpler. You can start from a simpler one. Usually we do not do that, I don't know. You usually don't start with the simple one, make it more complicated, yes? You start with the more complicated one and make it simpler. So here, I will start from the left-hand side, yes? So what can I do? I can cite that the left-hand side is equal to. So what is your suggestion? Have an eye on what you want to prove. You want to prove that this is equal to this one, and you see that there are no tangents involved on the right-hand side. So this motivates you to get rid of tangent in favor of cosine and sine, or something like that. Okay, so the thing comes to mind is that copy and paste one, get rid of tangent first step. What is tangent? Tangent is sine of the angle divided by cosine of the angle, and then a square. But we have an algebra rule. If I have two numbers divided, and I want to raise it to any power, the algebra tells me you are allowed to raise the numerator to that power, denominator to that power separately. So I do the same thing here. So this becomes the numerator squared divided by the denominator squared. So one rule of algebra is necessary here. This is the rule of algebra. Okay, but then you see that this cosine squared, I need it on the right hand side, it appeared, but I have to get rid of this sine squared in some way. There is no unique way to do it, unless I would say that, okay, I have the sum of two terms here, but on the right hand side I have only one single term, so it is a good idea to combine them, yes?
Couldn't you rewrite 1 as sine squared of theta plus cosine squared?
Okay, but that is not useful. Yes, I can. If you can take it, you can write sine squared plus cosine squared, and then you have this rest of the story, yes?
Yeah.
It is not wrong, but do you see, is it promising? Because my goal is to simplify to reach to this.
Yeah.
If you write this equal to this is 100% correct. But I would say 100% correct, but probably not helpful.
Sure.
Yes? So this is why I do not go for it. I would say that, okay, this is one term, this is second, this is two terms. So I have two terms. I want to combine them to make them one term. This is one good idea if I can do that. And then this is something very easy. If I give you a, 1, plus a fraction, I don't know, a over b. If I insist to add them, how do you do that? For example, instead of 1, you write b over b, and then you have a over b, yes? And then add the numerators. I will do the same story, the same idea here. So instead of 1, what do you think I will write?
Cosine squared x over cosine squared.
Yeah, exactly. So I would write cosine squared x over cosine squared x, and then I have plus sine squared and cosine squared. Yes? And then what happens, I can write cosine squared as the common denominator. The rule is to add the numerators now. So this becomes cosine squared x plus sine squared x. But then suddenly this famous combination appears, so that is exactly 1. This becomes 1 over cosine squared x, and that is the right hand side. Yes? So I was able to start from the left hand side, and then simplify things a little bit. Little by little I reach to the other side. So this means that, of course, this is meaningful if cosine is not 0. So as far as cosine is not 0, this equality is guaranteed. So where this equality is not valid, if this is the unit circle, yes, where the cosine is 0 is 0 either here, so I have to exclude this point, or cosine is 0 if I am here, because these are the only points at which the cosine is 0. So this is not necessary, this is not part of the problem, I'm just telling you because of deeper understanding. So this is valid whenever your angle is not at these 2 points. For every other point, this will actually work. Yes? Okay. And I would say that if you are interested, if you have some Anki, I don't know if this is going on, you can put this formula in your Anki as well, that's important. And by the way, if you knew about this identity, you can find another way for solving that prototype example here, yes. How? Because if I give you tangent, you take tangent and put it here, you find cosine. And then when you find cosine, you have tangent, you can find sine. So if you use this, that would be an alternative, I would say, solution for this problem. I recommend you go home and use this formula to again solve this problem and to see that you get the same answers again. And that's a good exercise to do, okay? So number 2. Let me give you another simple example. So number 2. This is chosen. This is, by the way, in the book. Let me give you another example from the book. So sine of theta minus cosine of theta totally squared plus 2 sine theta cosine theta is equal to 1. So here we want to show that this combination, regardless of the value of theta that I choose, is always 1. And I do not have any restrictions at all, because sine and cosine are always defined. They are not appearing in the denominator or so. This is every time. So it means that the domain of validity of this is every point on the unit circle. There are no exceptions. But again, this is simple. Let me do it for you. So how should I do that? I want to prove an identity. The best thing to do is to start from one side, reach to the other side. The complicated side is preferable. So I would say the right hand side, the left hand side is equal to, okay. What should I do? What is your opinion about how to solve this? Yes?
You can expand that.
Expand. Well, it's the only thing we can do, yes? So this is the first one squared. 2 times the first one times the second one. But because this is negative, it becomes negative 2 sine theta cosine theta. And then the second one squared is plus cosine squared theta. And then I will continue. So I would see that I know that some students will start repeating the identity over again. So I would, because this is writing so many things, assume that the right hand side is also a little bit complicated. So you have to rewrite the right hand side for no need, yes? So it is better to start from the left hand side. Don't put arrows, by the way. Arrows are wrong. Yes? So you put equality until you reach to the other side. Is it possible? Oh, by the way, I made a mistake here. Because this was just the expansion of the first part, there is an extra term involved. This is plus this extra term I have to write down. So 2 sine theta cosine theta. Yes?
Bobak, couldn't you
Thank you.
use single arrows?
No, not single arrows. There is no arrows. Arrows means from the truth of one thing, you are concluding the truth of another sentence.
Does the double arrow and single arrow mean different things?
Yes. But that's a different deviation to our topic now. Okay?
Okay.
That's a different. But anyway, you don't put arrows, yes? By the way, this is not something that I tell you. Arrow means something which is true implies something else. Okay?
Yeah.
And that's it. If I am a math teacher, then I like mathematics. Yes? This means implication. I am not implying something. I am just simplifying something. Okay? I am simplifying it. So it means that this expression, which is the left-hand side, I am not concluding this. I am saying that the left-hand side itself is equal to what I have written now, and it will be equal to what I will write further, so that I reach to the other side. So, okay? So what happens here? Then this one, whatever it is, I don't know, but that one and that one are just numbers opposite in sign, so they cancel out. And then, again, what is left for me? A famous combination in trigonometry, yes? Trigonometry. So you have to train your eyes to catch these patterns, okay? What's that? 1. And that's equal to the right hand side. Yes? I would write 1 and wait for you, because there is no way that I teach you what to do, yes? That's coming by experience. And there is also a PDF file from that American teacher. I will also upload that. The solutions are also in that file itself. So I did it for the equations, if you remember. I recommend you to try to solve those problems. If you have questions, you can ask me. So number 3.
Sine, cosine, trigonometry.
So let me think a little bit. So cosine to the power of 4x minus sine to the power of 4x is 1 minus 2 sine to the power of 2x. Okay? I want to wait for you a little bit so that you can think about how to solve the problem yourself. Okay? Do you have any idea? Yes?
Yes, so I started with what's called the conjugate.
Yes?
Conjugate rule, so that means that cosine to the power of 2
Exactly. So let me just start with that idea. So the conjugate rule, do you remember that was this pattern? Yes, if you have something squared minus some other complete square, if you want, you can factorize it in this form. This becomes this one minus that one plus this one. Yes? But so in principle, if I want to write all the details, so we start from the left-hand side. So you decided to start from the left-hand side because it's more complicated. I have 4 powers. Okay, so I would write it, if you want to be very actually rigorous, you need to write everything. So instead of cosine to the 4, I can imagine cosine to the 4th is cosine to the power of 2 to the power of 2 again, minus the same story for sine. Yes. And then you can give the role of the box to this one, and you can give the role of the circle to this one. If you do not look inside, then you have this pattern. So then it becomes what? It becomes cosine squared x minus sine squared x. And then again, cosine squared x plus sine squared x. Yes? But one part is famous. Yes? This one is that famous identity in trigonometry. So what is this one? 1. It is just simply 1. 1 times everything. Any number is the number itself. So this becomes cosine squared to this. So far so good. I would say that is a progress, because from 4th powers I reduced my problem to 2nd powers. So that is a good progress. But still, it's not that problem is not solved. You need to have an eye on what is going on the right hand side. If you look on the right hand side, I do not have any sign of cosines. Yes, it's I have only sine. Here I have a mixture of sine and cosine yet. So I have to get rid of, by looking on the right at the right hand side, you realize that you have to get rid of this cosine in favor of sine. To be more precise, you need to get rid of cosine squared in favor of sine squared. And then what's that?
It is 1 minus.
Yeah, just use that, because I told you that this identity, which is famous, can be viewed in 3 different ways. Yes, sine squared theta plus cosine squared theta is 1. Of course, you can write sine squared theta is 1 minus cosine squared theta, and you can write cosine squared theta is 1 minus sine squared theta. They are not 3 identities, they are the same. So this helps you to get rid of sine squared in favor of cosine squared. This helps you to get rid of cosine squared in favor of sine squared. Which one we need? We want to get rid of cosine squared. So I will use this formula. So instead of cosine squared, I am allowed to write 1 minus sine squared. Yes? This is actually this term. And then I copy and paste the rest. That's good. But then you realize that I have minus sine squared, another minus sine squared. So this means that what do I have? Which is this one. And that's equal to the right hand side. Yes, is that clear? Okay, let me write another one. So number 4. So number 4, let me write this one. Sine x over 1 plus cosine x plus 1 plus cosine x over sine x is supposed to be equal to 2, let me see, 2 over sine x, yes. Okay, if you don't mind, let me start solving this myself to explain things, and then I will give you a little bit harder but similar one to this one to work, so that you can work on. Problems at these levels are actually in the book, so it's not beyond what you need to learn. I think this might be A level. It's not that hard, but let us see. Okay, what is your suggestion? Again, you're supposed to prove an identity. It is preferable to start from the left-hand side, which is more complicated in this case, to reach to the other side. Of course, I see that there is a sine only here, no cosine there, but this is not a good idea to use this formula. Why? If you want to, so this is a natural, by the way, it's natural to think about to get rid of cosine in favor of sine. But remember, these formulas are helpful if you want to get rid of the squares, sine squared, cosine squared. Why is that? Because if you want to get rid of cosine here, This is cosine squared. So what you need to do, you need to take a square root. So this means cosine theta is plus or minus square root of 1 minus sine squared. Yes, you succeeded to get rid of cosine, but you make the problem, to be honest, harder. First of all, you have to solve problems in two cases, one with positive sign, one with negative sign, and then you have to live with this square root sign, which is more complicated. So even though it seems natural, but it is not practically possible. Okay, if this is not going to work, another scenario is to look at this thing. I have one fraction on the right, I have two fractions on the left. So is there any way to combine two fractions into one fraction? Yes, I add them. How should I add them? If I give you 2 over 3 plus, I don't know, 3 over 2, something like that. If you want to add these two, what you take, the common denominator is 6. And then you say 6 divided by 3 2 times, you multiply 2 here. 3 times 2 divided by 2 3 times, and you multiply 2 there, yes? So I would prefer to do it myself in this way. You can rescale them, but I think it's boring. Yes, so I would say left-hand side is equal. So what will be the common denominator between these two? So if you have forgotten the rational expressions with work in Math 3C, you can go and watch the videos. Yes? What's that?
It's 1 plus cosine sine x.
Yes, you just juxtapose them actually in this case.
Yeah.
By the way, you know that this is not always the most efficient way. In this case, yes, this is. You need to find the smallest one, which is divisible by all of. Okay, and then you would say that, okay, this fraction, the denominator has changed to this. How? By multiplying it by sine. You are not allowed to change something unless you also multiply the numerator by that expression. So this means that you take the numerator and multiply this by that extra factor. But this is a coincidence. They are all the same, so this gives you sine squared x. Understandable? And then you have this addition. You repeat the process. Sine x has changed to this by multiplying the sine x by this factor. You're not allowed to do that unless you rescale the numerator as well. So you just multiply this by its own numerator, which coincidentally are the same again. This becomes what? 1 plus cosine x totally squared. Yes? And then if you remember what I told you in Math 3C regarding simplification of algebraic expressions, rational expressions, it's better not to touch the denominator, because if you want to simplify, you have to factorize. It is already factorized, so don't take it away. Okay? So this means that you, by the experience, learn these things. You just copy and paste the denominator until to see what happens in the next stages. Okay? So what you need to do, you simplify the numerator only as much as you can. Okay, for sine squared, it's not very clear what we can do right now, just to copy and paste, but at least we know what to do with this one. I just square it. This becomes the first one squared, 2 times the first one times the second one, plus the second one squared, yes? And then you have to be always observant to catch the patterns. And immediately one pattern emerges, yes? This combination is famous. Sine squared plus that cosine squared at the end,
Yes.
which is 1. But you also have an extra 1 here. So that one will combine that one, it gives you 2, and then you have 2 cosine x, and the denominator again, you just copy and paste without actually multiplying it. Okay, so I hope that you understand that this cosine cannot be simplified with that cosine, yes? Because cosine is not the factor of the numerator. If I ask you what is this, you don't say it's a product, you say it's a sum. Sum of 2 terms, one of them is 2, the other one is 2 cosine x. Yes?
You factor 2 out.
Yeah, you can factor 2 out now. So what happens? You factor a 2 out. In the numerator, you will get 2 times 1 plus cosine x. And in the denominator, you have 1 plus cosine x n times sine x. Now, if I ask you, is the numerator a product? You would say yes, it is a product of 2 and this, 1 plus cosine. Is the denominator also a product? Yes, it's a product of 1 plus cosine and sine. So you see 1 plus cosine x is a common factor. Common factors are the only ones that can be simplified. And if you simplify that, in the numerator 2 is left, and in the denominator sine x is left. And that's exactly equal to the right hand side to the problem description. Yes?
If you would, for example, as an example, multiply both sides by 2 and then not convert back to the original, would that still be acceptable as an answer? Because what I did is I multiplied by like the common denominator, so I multiplied by 1 plus cosine x times sine x in that regard. So
No, you are multiplying both sides.
yeah, exactly, both sides.
I don't like that method.
Okay.
Because
it
that method...
still proves that it's possible, but it's not like it doesn't prove the original equation in the same way.
Yes, so this split, I don't like it because you have to be very observant. Of course, I cannot say it is wrong, but then in that case you have to use double arrows all the time. Because if you start, because what you are saying, you are changing the whole story and you got something which is correct. Okay? But then you want to say that, okay, now look, this is correct. It means the original one is also correct. This happens if you can make sure that at each step that you are continuing, you have double arrows. Double arrows means they are equivalent. Okay? So if you want to do this, you have to play according to the rules. Yes. If you want to use that method, I don't have any. I have some objections. That's a matter of taste. I prefer this one. But if you use this equivalency all the time, and so this means that instead of proving this, you are proving something else. From the truth of that something else, you want to conclude the truth of the original one. You can do it if you can show that every step is equivalent to the previous one. Is that understandable? Because, for example,
But in this case, I think
yes, if you multiply, you make sure that these are not zero. Yes, but you should say that they are not zero, because if they are zero, the denominators vanish. Something like that. Yes? I know, because many people are willing to write something like this, and then when it comes to the national exam, the people who write properly are deserve to get that A points. Yes? But logically, what you are doing is correct. So I cannot say this is wrong. Yes? But let me just give you some hints. So if I give you, for example, do you remember we had this? That was the source of false roots. So if when you want to solve root equations, if I ask you to solve this, apparently you are not doing something wrong. You raise both sides to power 2, and then you get x minus 2 is equal to 9, and then you get x is equal to 11. Okay? So from this step to this step is 100% correct. From this step to this step is 100% correct. From this step to this step is 100% correct, but it turns out that the answer is not acceptable. Because if you put 11 back here, square root of 9 is 3, not minus 3. So even though it seems that you are following the rules perfectly fine, but at the end you are getting something wrong. And then you might be wondering why this is happening, because I am doing everything correct. The reason is that this one is, so this one and that one are equivalent. This one and that one are equivalent, but this one only goes in that direction, not in the previous direction. So this tells you that the last statement and the first statement are not equivalent.
But this particular example isn't solvable without imaginary numbers, right? Or is it?
No, forget about that. Assume that I want to work with real numbers.
Yeah, but I was
This is telling you that 11 is an answer to this equation, which is a false statement.
But would we run into this problem in the national exam, for example?
I don't know, but I don't care about the national exams. I care about the legitimate mathematics. Yes? What I want you to understand is that if you want to do something like this, you have to make sure that every conclusion is not only going down, it is also possible to go backwards. Yes? And then, of course, it would be a big headache. Yes? So unless you really know the details what is going on, and then that's acceptable. Yes? Okay, and let me just, if you don't mind, let me write one here for you, wait for you. It would be of this nature. I want you to learn this. I just remind you about this common denominators and things, but it's a little bit hard, okay? And I want to wait for you. Try to learn it in proper way, okay? So let me see if I can find this. Yes. So 1 plus sine of alpha, let me write beta because alpha can be confused with. So 1 plus sine beta divided by 1 minus sine beta, and then minus the other way around. 1 minus sine beta divided by 1 plus sine beta. You are supposed to show that this is equal to 4 times tangent of beta divided by cosine of beta. Yes? So I want to pause recording and wait for you to think about this. Yeah, I would consider this a A-level problem, considering the standards in your book. Let me double check that I have done everything right. Plus, minus, minus. Yes, that's correct. Okay, so let us solve that so that we can. Do you know when the lesson ends?
No.
11:40. Yes. Yeah, 11:40. So let us at least solve one more problem after explaining this. So, what I am supposed to do here, I hope that you agree it's good to start from the left-hand side, which is equal to, okay, I don't know, what, based on experience you have gained so far, so what do you think I should do?
The common denominator.
Common denominator. And then, this is one of those cases, again, the common denominator is the product. Don't get used to this idea that always multiply, yes? Because, for example, if you have 1 over 6 plus 1 over 12, if you want to add them, of course you can take the common denominator, the product 72, but it is not efficient. The best common denominator between 6 and 12 is 12 itself. So if you write 72, it will work at the end, but it is not efficient. For this, it becomes sometimes horrible, okay? But in this case, I hope that you agree this is the least that we can write, yes? Okay, and then you would say the same story. This has turned into this by being multiplied by this expression. So I'm not allowed to change anything, so I have to multiply its numerator by the same factor, which turns out to be the same thing. So then it becomes what? Question so far? Okay. And then you see minus sign. Again, let me repeat. 1 plus sine beta has turned into this expression by being multiplied by this factor. You cannot do that unless you multiply its own numerator by the same factor as well, which is coincidentally again the same thing. This becomes 1 minus sine beta squared. And then by experience, I told you, do not touch the denominator for the time being, and then try to simplify the numerator as much as possible. So what is the method? To expand them. And if you don't mind, let me, for the time being, keep the pairs of brackets. So this becomes the first one squared, 2 times the first one times the second one, and then the second one squared, yes? And then minus, the same story for the second one, so this becomes minus 2 times sine beta plus sine squared beta. And then I remove the pairs of brackets here. The pair of brackets here, I can simply remove it because there is nothing behind that. So this becomes 1 plus 2 sine beta plus sine beta squared. But for the second one, you have to be careful that minus sign is for all the terms, yes? So minus 1 turns this one to this minus 1, and the second one becomes positive. And the third one becomes negative. Let us keep the denominator for the time being. But you see what is happening now. This sine squared beta and minus sine beta squared are gone. This positive 1 and negative 1 are gone. So you have 4 sine beta, 2 sine beta plus 2 sine beta is 4 sine beta. But then, do you have any suggestion? Now you know that nothing is simplified. If I just copy and paste them in this form, none of them can be simplified with that sign. So there is no hope if I want to keep this in the product form. Yes? So what's the answer?
You use the conjugate rule.
The conjugate rule. Some people start multiplying. That's not wrong. I will not roll deduct any point. But I want you to catch the patterns. Yes? This is a conjugate pattern. The answer becomes the first one squared minus the second one squared. Yes? But then again, this should be also familiar to your eyes. Yes?
It's equals to
Now you can tell.
cosine squared of beta.
Beta. This becomes 4 sine beta divided by cosine squared beta. So far, it's a very good progress because this was a little bit more complicated than we have right now. But the point is that's not exactly 100% what we want. But then it's not hard to understand, yes?
Yeah, then you have tan beta, that is
How?
sine.
So
Sine
if you want to
divided by
motivate me to do that, so you just write tangent beta. So let me write it in this way.
Yeah.
So sine beta,
You take out sine.
and then you can write cosine and then cosine, yes? But this part is what? Tangent. So you can just write 4 tangent,
Yes.
and what is left for me is cosine beta in the denominator, and that is exactly equal to the right hand side. Yes? So you see, one thing we had faced in the previous lesson with Natur students, I think, so if you want to prove A is equal to B, of course one way is to start from A, do some algebra and reach to B, which I am doing right now. But sometimes it is a little bit hard because both sides are complicated. So in those cases, instead of proving that A is equal to B, you can simplify this and prove that A is equal to C. You can simplify this and prove that B is equal to C. Instead of proving that A and B are directly equal, you can prove that A is equal to another quantity C, but B is also equal to that quantity C. If you succeed to do that, of course it is true that A has to be equal to B. Yes? Let me give you an example of this sort as well, so that we can see what we can do. So here I would write one more, and then probably we are done. I give you a little bit of time to think yourself first. So that my goal is to use this idea here. So let me write the question. So the question is 1 over sine x So we want to show that this is equal to tangent x So this question. I give you 5 minutes and then we start. Okay, so we don't have that much time. So let me start here. At least you might start from the left-hand side. Let us see how it goes. So do you have any idea how to do it in the left-hand side? I don't know which method you started, yes?
I think you can rewrite the first bracket as minus 1 over sine x.
No. Minus 1 over sine x, why?
Because
No, you cannot. It is like this. It is you have 1 over 3 minus 3.
yeah,
So there is only one way if you want to simplify, and that is just take the common denominator. That's the same story here. So, but the denominator here is 1. So what is playing the role of the common denominator here? Sine x itself. Sine x has not changed at all. So I do not change anything in the numerator. But 1 is now sine x. So it has been multiplied by sine x. I cannot do it unless I multiply its own numerator by the same factor. There is a minus sign here, and they are the same. So this is the correct way of doing things here. Yes? I will do the same thing without explanation for the next one. What is this operation here? That's a product. The same story. Instead of sine, I have cosine, so it will be the same thing. But then I told you that this should look familiar to your eyes. 1 minus sine squared is cosine squared. No, conjugate is right, but what's the point of conjugate? If you factorize it, then what? That's correct, not wrong, but useless, yes? But I told you that these patterns, you should be familiar with these patterns. 1 minus sine squared is cosine squared. So this becomes cosine squared divided by sine x. What about the other one? Sine squared, sine x squared divided by cosine x. You are multiplying things, you are multiplying fractions. The rule is to multiply the numerators and the denominators separately. But you will also learn that if you want, you can simplify these two if possible, which is not possible in this case. You should be able to simplify, not possible. But you can also simplify in cross-manner way. In this case, it is possible because one of these signs, I have two signs here. One of them is gone with that one, so what is left with is 1 sine x. The same story here. So what happens? It becomes simple, but it becomes cosine x sine x. That's what I'm saying. So we learned that, but this is the reason that I brought this example, because it is not that clear how to go from here now to the right hand side to make things a little bit more complicated. So what I say, if you are smart, you find a way, just go for it, but otherwise you don't need to spend so much energy on it. So you just write the left hand side is equal to cosine x sine x, and then you can put it in a box. For example, give it a number 1. And then you can start working on number on the other side. You would say that the right hand side is equal. Instead of tangent, what can you write? Sine x over cosine x. It's 1 plus the same story for the other one. Sine squared x, cosine squared x. Yes? My method is, because you see that you have a fraction, a bigger fraction, but the numerator and the denominator are also involved with partial fractions. Whenever this happens, I want to get rid of partial fractions as soon as I can. I would recommend you to also do the same thing. I rescale everything by cosine squared x. Yes? I multiply everything by cosine squared x. What happens? This term becomes cosine squared x. Okay, what happens for the second term? Can you tell me? Sine squared, because the cosine squared that I am multiplying will cancel this one. I am left with sine squared. And then here, I'm multiplying cosine squared. 1 cosine and 1 cosine are gone. 1 cosine is left, which becomes what? Cosine x sine x. If you want to do it, if you want, you can take the common denominator and then divide them. It takes ages, yes? But that's easier. And then cosine squared plus sine squared is 1. And then this becomes cosine x sine x over 1, which is the same thing as cosine x sine x. And then this is the proper way of writing, by the way. So you have to respect the way to write if you want to use this method. So the right hand side is cosine x sine x. You put it in a box, for example, and give it a number 2, and then you would say that from 1 and 2, we have, you see that the left hand side and the right hand side are equal to the same number. So this means that the left hand side is equal to what? Is equal to the right hand side. So sometimes it's also good to know this. Instead of thinking how I can go back, how can I go from this to that, which is what not very trivial here. You can stop there and start working on the other side with the hope that you are reaching to the same. Yes. Yes.
So the problem with long ago with my method wasn't that I changed the right hand side; it was that I changed both at the same time.
Yes. Yes.
So changing
Yes. No, that one is also okay. I just want you to understand there are some pitfalls there you have to be careful about.
But this is also preferable, right?
Yeah. So that is it. I will update the Google Classroom so that you have to practice a little. I will also upload the PDF file. The PDF file contains some more identities with detailed solutions. So if you don't know, you can just check. Thank you very much. Bye bye.